So we're going to be talking about acid-base reactions, but keep in mind acid-base reactions are just one of those three types of chemical reactions we're going to have. So we have the precipitation reactions, the acid-base reactions, the reduction-oxidation reactions or redox reactions. The precipitation and acid-base reactions dealt with that double displacement we talked about previously. Just a quick review of the double displacement reactions or metathesis reactions. In general, AX plus BY goes to form AY plus BX. All I've done is switch the anions around. In order for a metathesis reaction to occur, we have to either form an insoluble solid, that deals more with precipitation type of reactions, or we have to form an insoluble gas or a weaker non-electrolyte. The insoluble gas and the weaker non-electrolyte, those are going to be more involved with these acid-base reactions and formation in end products. Okay, so with acid-base reactions, we're going to take an acid and a base, mix them together, and they're going to form typically water and a salt. Okay, so HCl plus NaOH is going to form H2O liquid plus NaCl. Now with acid-base reactions, without any sort of indicator in there, it's really hard to see that any reaction has occurred. With precipitation, we see a solid formed. Here, what are we forming? Well, we're forming water, and we're forming a soluble salt. So, since we're dealing with aqueous solutions, and aqueous means dissolved in water, it just looks like we're mixing two water solutions together and just getting another water solution. It doesn't look like a chemical reaction has occurred, but in fact one has. Okay, because we formed that H2O liquid, that's a weak electrolyte. Means a reaction has occurred. So with acid-base reactions, we're going to have a little bit more problem having some sort of visual indication that we've had a reaction occur. We'll talk about that a little bit later when we get to titrations, where we add an indicator to actually see those changes. Alright, so keep in mind with acids and bases, acids are going to create H plus in water by definition. So if we look at HCl, HNO3, the H3CO2H, that's actually just acetic acid. It's just a different way of writing that HC2H3O2. Lemons have the citric acid. Vitamin C is actually an acid. We also have to be able to identify whether we're dealing with strong or weak acids. Strong acids are going to end up being strong electrolytes. They're going to completely ionize in water. Weak acids are going to be weak electrolytes. They're going to partially ionize in water. Okay, so like HCl, HNO3, those are strong acids. Acetic acid, the citric acid, the vitamin C, those are weak acids. HF is a weak acid. Okay, but the main thing right now, you need to know it creates H plus in water. With bases, we're going to say they're going to create OH minus in water. Some examples of those: sodium hydroxide, NH3 is ammonia. We've got Drano, we've got milk of magnesia. Those are all bases. Okay, well, we have to deal with strong versus weak with the bases as well. So strong meaning it's going to be a strong electrolyte, it's going to completely ionize in water, and weak meaning it's going to be a weak electrolyte, it's going to partially ionize in water. So sodium hydroxide would be a strong electrolyte. Ammonia, NH3, would be a weak electrolyte. The Drano is actually a strong electrolyte as well. Right, and there's a lot of other examples out there. The main thing you need to get with the bases, it's going to create OH minus in water. Alright, so here's some names and formulas of some common acids and bases. You should be able to, from the naming rules that we talked about already, you should already be able to predict the formulas given the name, or given the formula, write the names of these. Knowing which ones are weak and which ones are strong, it wouldn't be bad to know that acetic acid, hydrofluoric acid are weak acids, and ammonia is a weak base. Everything else on this table, those are strong electrolytes. Now something else we have to look at when dealing with acids and bases is something that you may not have run across before, and that's something dealing with amphoteric compounds. So like sodium bicarbonate here, baking soda. With amphoteric compounds, they can act as both an acid or a base, depending upon what's added to them. So if I take sodium bicarbonate and I add an acid to it, I get this chemical reaction occur. NaHCO3 plus HCl goes to form NaCl and H2CO3. Now everything is listed as aqueous, supposedly there's no reaction there. This is an important thing you need to know. Anytime you form H2CO3 as an end product, that H2CO3 is going to decompose to form H2O liquid and CO2 gas. H2CO3 is carbonic acid. That's what actually gives the fizz to your soda. What happens when you open a soda the first time? Well, you actually hear some of that gas coming out. Well, that's because H2CO3 is decomposing to form that CO2 gas. If you leave a soda open for long periods of time, eventually all the H2CO3 gets converted to water and CO2, and you have no bubbles left. And in fact, it tastes watered down. Part of the reason, you're actually forming water. So really what this reaction should look like is taking those two reactants and forming NaCl aqueous, H2O liquid, CO2 gas. Now what happens when I add a base to the NaHCO3, the sodium bicarbonate? Well, now I form sodium carbonate and water. Water is a liquid, so we have a chemical reaction occur. So when I add an acid, the sodium bicarbonate acts like a base. When I add a base, the sodium bicarbonate acts like an acid. I can have reactions occur with either one. That's what makes it amphoteric. So keep in mind, this is a picture of that process. Keep in mind, anytime we form H2CO3, it's going to decompose to form H2O liquid and CO2 gas. We get a gas evolution reaction from that. Gas is one of our products. That means we had a chemical reaction occur. Now keep in mind, evolution of gas doesn't occur with just acid-base reactions. We'll actually see it in reduction, oxidation, or redox reactions. All right, another thing about acid-base reactions, they're sometimes called neutralization reactions. Because we go from an acidic and basic solutions, when we combine those together, we end up with a neutral pH. We end up with water formed plus a salt. Okay, that's why it's sometimes called a neutralization reaction. All right, so let's look at some examples of predicting products from this. Now we're going to treat it just like we did the precipitation reactions. We can break these up into their ions, swap the ions around, combine the new ions into balanced formulas, and then predict their states. Okay, well when we do that, we end up with H2O liquid and BaCl2 aqueous. And I'm not going to go through all those steps. Okay, once we're done with that, then if we want, we can write the balanced equation of that. Let's look at another one here. H2SO4 plus MgOH2 solid. What are we going to form? We're going to form H2O liquid plus MgSO4 aqueous. When we balance that, we just need a 2 in front of the water. Now the other thing we do want to be careful of, we should be careful and should be checking those salts that are formed to make sure those are actually aqueous and aren't forming solids as well. Sometimes you can actually form a solid as well as that liquid water. So acid-base reactions are going to be relatively simple, especially if you know how to do the metathesis reactions really well. All we're dealing with is that H plus and OH minus. So with these reactions, you're going to form a water and either a salt or a gas product. But water is always going to be there. The other thing to keep in mind, you're going to have to be able to write the ionic equations for these reactions as well. So the molecular equation, complete ionic equation, net ionic equation. I'm not going to go through those because we've gone through those previously, but you need to be able to do that. All right, one last example. If I have HCl plus Na2CO3, we'll form H2CO3 aqueous plus NaCl aqueous. But remember, carbonic acid was formed, so we want to break that up into the water liquid and the CO2 gas. And then when we write the balanced version of this, we end up with that. Again, though, remember, you're going to have to be able to write all the ionic equations for these. So keep that in mind. Okay, so a real common use of these acid-base reactions involves something called a titration. Right? An acid-base titration is used to find unknown concentrations of an acid or base solution, so an unknown molarity. All right, so if we look at this, we're going to have a solution in the flask. We're going to have a solution up top in what we call the burette. Okay, a lot of times we're going to put the base solution in the burette, and it's going to be of known concentration, but we could do it with an acid solution too. We could put an acid solution of known concentration in the burette. Then in the flask, we'll have our acid solution, which will be an unknown concentration. So depending upon how these switch, we could have acid of known concentration in the burette, base of unknown concentration in the flask, and be titrating the base solution. Okay, in this example though, base solution is in the burette, it's known concentration. Acid solution is in the flask, it's the unknown concentration we're trying to determine. So at the start of this titration, what we have in the solution down below is we have an excess of acid. Now, the other thing that's missing here is we've added something called phenolphthalein, which is an acid-base indicator. Remember back when I said when we have acid-base reactions occur, we have nothing visual to see to help us indicate that a reaction has actually occurred. Okay, well, what we do is we add this indicator, and this indicator is going to change color depending upon what the pH of the solution is. So under acidic conditions, it's going to be colorless. Under basic conditions, it's going to be pink. So as we start to add that base into the acid, you can see in the second picture there, you can see some pink down in that solution a little bit. Okay, that means we're starting to see that chemical reaction occur. And what we're going to do is we're going to add base until we completely react with all of the acid. In other words, we neutralize that acid completely. That's what we're going to call the point of neutralization. That's also going to be something called the equivalence point. Now, with the equivalence point is going to be the point at which we've added just enough base to completely react with all of the acid. So technically we have a neutral solution, and technically that solution is still going to be colorless because that indicator wouldn't turn pink until it was basic. Okay, but that's at the equivalence point. Now, in order to get that visual cue to see that we've actually reached the end of our reaction, we add like one more drop of base, and that'll be enough. And that'll be enough to take us onto the third picture, where we're going to end up with a slight excess of base in solution, turns the solution pink, and we have what we call our endpoint. So our endpoint is going to be a way of predicting what the equivalence point should be. But equivalence point and endpoint aren't going to be exactly equal. Endpoint is going to be slightly off from the equivalence point. That's the basic idea behind an acid-base titration. So with the burette then, we can measure how much base solution was added to reach the endpoint. We knew how much acid solution we started with. Knowing all that, we can do a calculation to determine the concentration of the acid in solution. Now, one last thing to keep in mind, you can actually do titrations with the redox reactions as well. Okay, we're not going to go through that. We're only dealing with acid-base titrations, but don't look at a titration as strictly limited to just acid bases. Okay, but let's look at a calculation involved with this. So let's say I take 50 milliliters of an unknown H2SO4 solution. I put that 50 milliliters in the flask, and then I titrate that solution with 0.1523 molar sodium hydroxide solution. That goes in the burette. I start adding that base, and I keep an eye on when the reaction reaches its endpoint. In other words, I've reacted all of the acid. To get to that point, it requires 27.54 milliliters of the sodium hydroxide solution. So now the question is, what's the concentration of the unknown H2SO4 solution? Well, when looking at this, I'm having an acid-base reaction occur inside my flask there, so I need to have a balanced equation, and this is what the balanced equation would look like. The next thing I need to think about is if I'm trying to get the molarity of H2SO4, I need to know how many moles of H2SO4 I had in that starting flask, and I need to know how many liters of H2SO4 I had in that starting flask. Well, from the problem, do I know either one of those? Yeah, I do. I know that I started with 50 milliliters of solution, so I know my liters of H2SO4 solution is 0.05 liters. So all I need to figure out is then how many moles of H2SO4 were present in that solution. That's going to come from that other information involving the NaOH. So there's my balanced equation again. So I need to get the moles of H2SO4. What I have information about is the NaOH. Keep in mind, anytime I'm trying to convert between two different compounds, I need to use that mole-to-mole ratio given from the balanced equation. So I've got information about my NaOH. I've got the 27.54 milliliters of NaOH solution. I need to get that to liters. I can then use the molarity of that solution to get how many moles of NaOH I added. That's 4.194 times 10 to the negative 3 moles of NaOH. From the balanced equation then, I can convert those moles of NaOH to moles of H2SO4. And that'll give me the 2.097 times 10 to the negative 3 moles of H2SO4. When I plug those moles in for the moles of H2SO4 above, divide them out, and I end up with a concentration of 4.194 times 10 to the negative 2 molar H2SO4. That's the concentration of my unknown acid. So we walked through the steps of an acid-base titration, and we walked through an actual calculation where we determine the unknown concentration. You need to be able to do both of those. It's going to be very, very important. But with all these calculations, they still focus around paying attention to those units and recognizing the only time I can convert between units of one compound to units of another compound is if I'm using moles. And that mole-to-mole ratio has to come from a balanced equation. I couldn't convert milliliters of H2SO4 to milliliters of NaOH. I can't convert grams of H2SO4 to grams of NaOH directly. I have to use that mole-to-mole ratio. That's going to be it for the acid-base reactions.